So Dr. Swaminathan is currently working as an assistant professor in the discipline of electrical engineering, IIT Indore. And earlier, he completed his PhD from IIT Kharagpur in 2016 and also worked as a postdoctoral research fellow at Nanyang Technological University, that is NTU, Singapore, for 3 years between 2016 to 2019. So he has received his BTech degree from Sastra University and subsequently MA degree from College of Engineering, Gundi. In fact, I just happened to see that he also received the gold medal from College of Engineering, Gundi, Anna University. His research interests include efficient design of space air ground integrated networks, hybrid optical RF networks, which is a very hot topic. Non-line of sight ultraviolet optical wireless communications, development of novel algorithms for blind parameter estimation of forward error correcting code and interleavers, 5G and beyond wireless systems, which is the theme of this FDP, and so on and so forth. You can see he has a diverse set of specialization or areas in which he is specialized. And one of the areas I noticed here was intelligent reflecting surfaces aided wireless communications. So at a personal level, that is an interesting topic, which I believe is coming up in a big way. So we have a distinguished speaker here who has knowledge across domains in the area of wireless communication systems. He is also the author or co-author of 16 international journal publications, including IEEE Transactions, and he has been serving as a reviewer for reputed IEEE journals and also as a TPC member for various reputed conferences. So with that, sir, I welcome you, and I request you to take it from here. And I also, in fact, thank you at the outset for consenting to be a resource person for this FTP. So I'll stop sharing my screen now, sir, and you can take over.
Yes. So I hope I'm audible to everyone, and good morning, everyone, for this course. Especially, I hope the audiences are getting benefited out of this course from other distinguished speakers also for the past 1 or 2 days. I believe whatever I'm going to speak today probably give you some idea about the channel coding, which is currently being incorporated in 5th generation communication. So it will be, I believe, I assume only a very limited basic knowledge on digital communications for this lecture, especially for 1 hour 15 minutes or so to follow. So I assume a preliminary knowledge on digital communication. That is fine. I hope at least it gives you some idea on the channel coding techniques, which is being currently employed for 5G communications indeed. So I'm going to share the screen, and I'm going to start presenting it. Let me see. So is it visible? Is it visible, sir?
Yes, sir.
Yes, thank you.
Yes, sir. Please go ahead, sir.
Okay, thank you. So probably I will also write in the presentation whenever which is required to explain a few more things for better understanding. I hope you could able to even follow what I'm writing. I hope that is also visible to you. And yeah, today's topic, as I've already mentioned, it is channel coding in 5G communication. And this is the current outline of the presentation which I have planned. So basically, a first slide will be related to possible research areas, which in 5G communication, which indeed you would also be very much familiar at this point of time, as this FDP has already started on 23rd itself. And then I'll be speaking for continuity's sake about the channel capacity, then entering into the channel coding. Why is it important for especially for 5G communication, indeed for a digital communication or indeed a digital storage system, why channel coding plays a vital role. And I will be talking in general or some details I will be definitely giving about LDPC codes, which is low density parity check code, low density parity check code, which plays a vital role in 4th generation systems, as well as which is proposed as one of the important coding techniques for 5th generation communication schemes, communication systems. It is low density parity check. That's what Ldpc stands for. As well as I will be giving a few details regarding the encoding and decoding techniques, which is being proposed for polar codes. And I will be giving you the references which I have taken these topic from, so that you can also go through those references and get benefited out of that. So research areas in 5G communications, I don't want to spend much time on that. The main objectives of this 5G as well as beyond 5G and beyond wireless systems is to cater massive number of devices, to satisfy very high data rate, very high capacity, high reliability and long battery life. And in the right side, I have mentioned few key techniques or the physical layer technologies which are being currently proposed for achieving these objectives. A few of these techniques or technologies are massive MIMO schemes, where you'll be putting multiple antennas, not just multiple antennas, massive number of antennas to take care of this high data rate, high capacity, as well as to cater massive number of devices, as well as you will be moving, though probably the initial version of the 5G might work in the sub-6 gigahertz, which is microwave-based frequency range, but there is also a proposal that the millimeter wave frequency communication is also going to get possible out of this 5th generation. So you're going to move up in the band. Anyway, there are a few challenges when you're going up in the band, but still you will be getting benefit of high data rate and high capacity out of this. So that is, and Dr. Shahjahan Kuti is also very well versed in this millimeter wave communication. He has published a few good articles, including communication surveys and tutorials, has also been published in this millimeter wave communication, which comprehensively listed what are all the research areas or research topics which are being carried out in this millimeter wave communication. I also urge you to look into that. Apart from that, innovative channel coding schemes, including Ldpc and polar codes, that is also being proposed. That is mainly to take care of this reliability aspect. And then energy harvesting and NOMA, that is non-orthogonal multiple access techniques, is also being, especially NOMA is going to play a role, but I don't know about the energy harvesting. Might be applicable for a 5G and beyond wireless systems, but 5G communications already in 4G in one version, this NOMA is being incorporated as MUST, M-U-S-T. So kindly go and look for it. It is a superposition transmission. That is what multi-user superposition transmission, I think. So this is also being incorporated. This MUST technique is similar to that of NOMA, which has already been incorporated in one version of the 4G communication. However, it is going to incorporated in the 5th generation communication also as a non-orthogonal multiple access. Basically, you will be we will be using a power domain multiplexing in order to cater the massive number of devices, as well as to improve the battery life. Because of this grand free access nature, this is going to improve the battery life of the nodes which are going to communicate, especially for the IoT based nodes. This technique is going to play a major role. Okay, so now moving into the basic Shannon's capacity, I will be discussing briefly about Shannon's capacity, so that you'll be on the same page when I'm introducing channel coding and what is the purpose of channel coding. Okay, so without giving much more details, so everyone would have come across this Shannon's well-known formula, which relates the channel capacity with the bandwidth and the signal to noise ratio as B log 2 of 1 plus SNR. But how he achieved or how he obtained this, probably we are going to see briefly. But before that, he actually stated, he's the one who stated that a code, basically a code in the sense it's a channel coding, it with a large code word length will be proposed or will exist that achieves this data rate R closer to this capacity with arbitrary small error probability. That's what he stated in his theorem, which is noisy channel coding theorem. So given a bandwidth and a signal to noise ratio, how much data you could able to pump in in that channel, okay, with arbitrarily low probability of error. That is what it gives. That what the Shannon capacity gives that information. And basically, what are all, the current generation wireless communication systems? Basically, they transmit the data rate R, which is less than C, so that to be on the safer side, you would be communicating this much of information with the higher reliability. Okay, basically they will be transmitting with the rate less than C. So he has also mentioned, so it is possible, the C, that R equal to C, you can pump in with the data rate equal to the channel capacity or with arbitrary less probability of error. It is possible with the innovative channel coding techniques with the higher block length. So he has envisioned it before while he proposed that there will be a code, okay, with a higher block length, which will satisfy that you could able to pump in with the rate equal to this capacity C with arbitrary low probability of error. That indeed kind of probably made the researchers to develop codes that can achieve this capacity C. They can able to transmit with the rate equal to this channel capacity with arbitrary less probability of error. Say, for example, 10 to the power of -5 or -6 is what is they are looking for when they are speaking about arbitrarily small probability of error. Okay, so the research have been started. So many coding schemes have been proposed: block codes, convolutional codes, and different versions of block codes, and then turbo codes, which is a parallel concatenation of turbo codes, which is a parallel concatenation of recursive systematic convolutional codes, and then comes Ldpc and polar codes. Mainly, it is to address this whether I could able to send the data rate equal to the Shannon capacity with the arbitrary less probability of error or not. So that is what is the main objective, and that is what is being set as a benchmark when they are proposing these kind of codes. So and then it would have been mentioned that this capacity achieving code means the code or error correcting codes which helps you to achieve the Shannon capacity. That's what it means as capacity achieving code must be sufficiently long. That's what I have mentioned. And then see, conversely to state, if you are trying to transmit with the rate above the Shannon capacity, obviously the error probability will not be arbitrarily low. It would be bounding away from zero. That you would be facing a lot of errors, so that the objective of reliability, higher reliability, will not be satisfied. Okay, so to continue further, so what? 1 minute, it's not moving. Yes. So to continue further, so this is what is the Shannon capacity C. Basically, it is for general Shannon capacity, that is maximizing the mutual information over all possible input distribution P of X. Okay, mutual information, I hope you might know something about mutual information, which is the expressions which is given over here, and in terms of entropy also it is defined over here. So you have to maximize this mutual information, the maximum of this mutual information, which you're obtaining by maximizing over all possible input distribution. That value is what is the Shannon's capacity. So for AWGN channel, it turns out to be that this input distribution which maximizes the capacity is Gaussian. And if you compute this relative entropy, and then if you obtain this mutual information, and after subsequent steps and derivations, you would be obtaining this expression B log 2 of 1 plus SNR. So you have to note one point: Shannon capacity C is equal to B log 2 of 1 plus SNR, provided the channel is AWGN. Okay, so it differs if the channel is a binary symmetric channel, binary erasure channel, so it differs accordingly. So that's what is the point which I would like to make. Okay, so now, so moving into the topic of channel coding. So it plays a very integral part in every modern digital communication systems, indeed wireless communication systems, also in storage systems. So in order to, this channel coding schemes will help you in detecting as well as correcting the errors from the received information symbols. Okay, so if this coding scheme is detecting as well as correcting the errors, it helps to improve the reliability or the performance in terms of bit error rate. That is what is the objective for this channel coding. Basically, you should not confuse this with the source coding. Source coding is to compress the data and then send it, removes the redundant information and compresses it, and then it sends the information, whereas channel coding basically adds redundant data to detect or correct errors. How the redundant data gets added, probably we will be seeing. So it adds redundant data or redundant bit information with the information bits, which helps you in detecting as well as correcting errors. So basically, channel encoder involves two blocks. One is this forward error correcting codes. So forward error correcting codes, that is what is channel codes. Okay, so error correcting codes as well as it is followed by the interleaver. Okay, so this error correcting codes, forward error correcting codes will take care of correcting the random errors, as well as this interleaver will take care in correcting the burst errors. Basically, burst means series of errors which will be happening. Okay, so for example, 100 bits in a series will be received with errors. So that can be taken care by properly interleaving the data after performing the channel coding. So that burst error corrections also can be taken care of using various interleavers. For example, block interleaver, convolutional interleavers. There are so many interleavers. So these two blocks generally if a channel encoder is being involved, it is always it comprises of FEC encoder, that is forward error correcting code encoder, followed by interleaver. So this takes care of correcting the random errors, and this takes care of correcting the interleaver, which is burst errors. Similarly, in the channel decoder side, you need to de-interleave it, and then you need to decode it. Anyway, now first I will speak about the basic linear block codes. So this is one kind of a channel coding scheme, which is various different kinds of block codes have been proposed, such as BCH, RS codes. Indeed, Ldpc codes will also fall under the category of this linear block codes, where a block of information bits, say M1, M2, M3. So a block of information bits will be converted into a coded bits, say M1, M2, M3, and you will be adding parity P1, P2, P3, such that so this block of information bits M1, M2, M3 is being converted into a coded bits, which is M1, M2, M3, and then you are adding parity P1, P2, P3 based on this message information bits. So subsequently, you will be having series of message bits. You will be converting those message bits into block of, say in this example, I have taken into consideration block of 3 bits. This block of 3 bits, it will be converted into a coded bits, which is of length 6. So every block of 3 bits will be converted into, say, a block of 6 bits. So that falls under the category of 6,3 block code. So this 6 is nothing but the code word length, and this K is nothing but the message block length. Okay, so so just to give an additional information, or again to motivate you, this message symbols, basically I would say it as symbols, because this bit information will be converted into symbols after modulation. Say if you're employing Bpsk scheme, you would assume it as, say, 1 minus TB, where B is this bit information. So this 0 will be converting into, if you substitute 0 as B, so this 0 will be converted into symbol 1. Again, 0 will be converted into symbol 1. This 1 bit will be converted into symbol -1. And similarly, this 1 will be converted into symbol -1, 0 will be converted into 1. So this 1 over here, which I have written, this -1 and 1, they are symbols. They are symbol information, and they are not bit information. So that is to be noted. Okay, so these message symbols, if it is being transmitted through the noisy channel, this message symbols or bits might get flipped. Flipped in the sense this 1 will be decoded as -1, or this -1 will be decoded as 1. So to correct these errors, up to certain limits, you can correct these errors. Sorry. So up to certain bit information, you can correct these errors. For every message block, you can correct 1 or 2 bits depending upon the coding scheme which you have been employed. So, so to correct these errors, some redundant bits are added to the information sequence. What are all these redundant bits? This is what is called as the parity bits. You are adding subsequently P1, P2, P3 with your message bits M1, M2, M3, which helps you in correcting the errors. And to give some view on the vector space view of this coding, so this message M is a binary sequence of size K. So you can see it's a size K. In this example, we have assumed K equal to 3, and it corresponds to a K dimensional space. So K means you can see all possible 2 to the power of 3 combinations. So 8 possible combinations of message bits will be there, and this you can view it as a k-dimensional vector space, that is 3-dimensional vector space in this case. 3-dimensional vector space means you should have 3 basis vectors to span that vector space. That is what it is, k-dimensional space. So this all possible combinations of this message bits, you can view it as a k-dimensional space. And then you could see that this code word C, okay, will be generated corresponding to each message bit M. Okay, for example, 000 will be corresponding to 000 and then 000. So I will give you information how to correct a 3-bit sequence into a 6-bit code word. So I will give that information probably in the next slide. Similarly, this 111 will be converted into another 6-bit code word by adding 3 redundant bits. And after converting into n-bit code word, okay, this code words will be corresponding to another space, a vector space, which is an n-dimensional space. It is a part of the n-dimensional space. Okay, that is what you could say, that you could see that the k-dimensional space is getting converted into code words in the n-dimensional space. Okay, and there will be one-to-one correspondence. For example, 000 will be coded as this one only. No other information bits will be coded as 00000. Okay. Similarly, if 111 is coded as, say, some 6-bit information, no other information bits will be coded corresponding to that particular code word. That is what it is, one-to-one correspondence, as also indicated in this particular diagram. So you are transforming from a k-dimensional space, okay, a 3-dimensional space in this example, to a 6-dimensional space, which is n-dimensional space. Okay, so how to transform that? Yes, you can do it using a generator matrix, which is of size n comma k. It is not a column vector. Remember, this G0 is a row vector of size n. It is a row vector of size n. So basically, using a generator matrix, you could able to transform your message bits, a 3-bit or a k-bit message bit, into an n-bit code word using this relation C. That is the code word which is equal to M. M is nothing but your M0, M1, Mk minus 1. K is the message block length, and then multiplied with this, this would be a k cross n generator matrix. Sorry, k cross n generator matrix. So if you multiply it, you would be getting an n-bit code word length. Basically, a vector space point of view, if you want to give these row vectors are the basis vectors, and the linear combinations of these basis vectors will be spanning that subspace. Basically, this code words will be forming a subspace inside this n-dimensional space, which is a k-dimensional subspace inside this n-dimensional vector space. Anyway, I don't want to go much further into this vector space point of view, as I may not be. This is another point of viewing these code words, especially if you are from a mathematics background. It can be viewed as this code word. Indeed, see, there will be 2 to the power k message bits, and this 2 to the power k message bits will be corresponding to 2 to the power of k code words. And these 2 to the power of k code words will be a part of this n-dimensional vector space. Because this 2 to the power of k code words, each code word will be having a length of n. So definitely it will be a part of the n-dimensional vector space. Okay, so so that's what I have mentioned over here, that an n comma k linear block code, okay, is a k-dimensional subspace of an n-dimensional vector space. Even if you are not getting this point, fine. So it is not a problem. You could able to at least get an information that this message, which is of block length k, will be converted into an n-bit code word using this generator matrix. And this generator matrix will be a k cross n matrix. All the rows in that generator matrix should be linearly independent. That is a rule. Okay, it should be a rank k matrix. It should be linearly independent, so that this criteria of k-dimension subspace would get satisfied. Okay, you should have k at least linearly independent vector to span this k-dimensional subspace. Anyway, it is of size k cross n, and you would get the code word C by multiplying the message block length with the generator matrix. Okay, so basically it is a block code. You can understand about that point, because each message block of size k is getting converted into an n-bit code word. That is why it is block code. Block by block it is performing the coding, as well as there is an additional word which is linear, because it is the linearity property is satisfied. What is that linearity property? Sum of any 2 code words. Remember, there will be 2 to the power of k code words. So that if k is 3, for possible 8 message bits, you will be having 8 code words, right? That is what is 2 to the power of k code words. And among these 8 code words, okay, the sum of any 2 code words will also be another code word. Okay, that is that if you are transforming with these rules. What are all the rules? This G should be a K cross N matrix, and K should be K vectors, row vector should be linearly independent, and the linear combination of this, basically if you multiply M times G, you will get M0 G0 plus M1 G1 up to MK minus 1 GK minus 1. This is nothing but the linear combination of linear combination of the row vectors, right? Row vectors. This is a linear combination of these row vectors. Okay, so it gives this, if you are performing M0 G0 plus M1 G1 MK minus 1 GK minus 1, remember this G matrix will be fixed for a particular code, say n comma k, 6 comma 3 code, or 7 comma 4 code. This G matrix will be fixed. What will be varying? Obviously this M0 M1 MK minus 1 will be varying. Accordingly, you will be generating 2 to the power of k code words. This linearity associated with the fact that the sum of any two code word is also a code word. Also, all zero vector is also a code word in every linear code. These two properties also should be satisfied in order to say it as a linear block code. Okay, so that is one set of code which you would have understood as a block code. There is also another set of another branch of code, okay, which is a convolutional code where it involves memory. Previously you would see that say if you're having M1, M2, M3, this will be encoded as say M1, M2, M3, P1, P2, P3, and then the next message block, say M4, M5, M6, this will be encoded as M4, M5, M6, P4, P5, P6, where this M1, M2, M3, this message block will not influence the next code word. Basically, M4, M5, M6, okay, basically the second code word will be depending on only the next 3 message bits. It doesn't depend on the previous message bit. However, in case of convolutional code, there is a shift register or a memory-based encoding is involved, where the previous bit information will also influence your next code word. Okay, so I don't want to go much into the details, just I will give you one example of a convolutional encoder, which is 2, 1, which means n is 2 and k is 1. For every one message bit, you would be getting 2 message outputs, and this 3 basically implies the number of shift registers involved. Okay, especially if it is k equal to 1 code, k equal to 1 message block of length 1. Okay, if that is the case, then this capital K, that is nothing but this 3. Basically, you will represent it as nk and capital K. N is the code word length, K is the message block length, and capital K is the constraint length. Okay, when K equal to 1, this capital K implies the number of shift registers involved. Okay, so you can if the message bit is say 100, so first 0 will be entering, and the other 2 shift registers probably would have been loaded with the pre-data, or you would assume it as there is a 00 which will be existing, and the 7, 5 basically it specifies the connection between this shift register and XOR. Okay, so 7 implies all these shift registers are getting connected to the XOR, that is 111. So octal version of 111 is nothing but 7, and in the below part it implies 101, right? There is a connection towards the first and the third shift register, but there is no connection, so that is 0. So 101, the octal version corresponds to 5. So 7, 5 indeed implies the connection between this shift register and the XOR gate. And you could see if the bit information 0 is entering into the first shift register, assuming that the other 2 stages of the shift registers are 0, then you could compute you could XOR it. 0, 0, 0 will be XORed, and the first coded bit will be 0. Similarly, 0, 0, 0, 0, this first and then the third 0 will be XORed, and that will also give 0. So corresponding to 0, it gives 0, 0. Similarly, the second when this input bit is entering, this first bit will be moving to the next stage. Similarly, when the third bit is entering as 1, then these 2 message bits will be entering into the subsequent stages, and accordingly you would be generating the coded bit. So what it implies is every 1 bit information, when it is entering into the shift registers, it is giving you 2 message bits output. So it is a memory based coding. Yes. Now entering into the low density parity check codes. This is, as I've already mentioned, this is being currently employed in 5th generation communication, and it is one sort of it belongs to the family of linear block code. Basically, any block code, if you see, they can be specified in terms of either generator matrix. Given a generator matrix and the message information M, you could able to generate the code word as M times G. Okay. Also, it can be specified in terms of a parity check matrix. Now, I'm giving you another matrix, like how G is a generator matrix which helps you in generating the code, and H is another matrix which is a parity check matrix which is orthogonal to G. So H is orthogonal to G. Okay, which means that whatever the vectors, row vectors, or indeed the space which is spanned by H, that will be orthogonal, means the inner product of these vectors with this G vector will be giving you 0. Okay. There is another parity check matrix which should satisfy the property that C times H transpose will be equal to 0. This constraint should be satisfied, then only you would say it as a linear block code. So you can able to see that even this code can be specified using a parity check matrix using this constraint C H transpose is equal to 0, and this constraint is what is called as a parity check constraint. Okay, and this H will be an n minus k cross n matrix. How G is k cross n matrix, this H will be an n minus k cross n matrix, and remember the point that it should satisfy whatever the code which you are generating, that should satisfy this constraint C H transpose is equal to 0. That is what is the additional information which I can give about a parity check matrix, which will be there for every code. Okay, but there is a specific property for this parity check matrix, especially in case of this low density parity check code, which is nothing but the name itself implies the low density. That implies the parity check matrix which will be involved in this is nothing but a sparse parity check matrix. Okay, sparse means probably very minimum non-zero non-zeros will be there employed in the parity check matrix. Say if it is a binary code, then only very minimum number of ones you will see inside this parity check matrix, and mostly the parity check matrix will be probably it will be loaded with zeros. Okay, so that is what is the sparse nature, and sparse also implies it is low density. Okay, so since the parity check matrix involved in this Ldpc code will be having only very minimum number of ones, okay, or non-zero symbol, so that is why it is called as a low density parity check matrix, and the code which is defined by using this low density parity check matrix is what is called as a low density parity check code. Okay, so it follows this criteria. A regular Ldpc, there are two kinds of Ldpc which I will be coming, a regular Ldpc and irregular Ldpc. What we are going to see that this n implies the message code word length, and wc it implies the number of ones in the columns of this parity check matrix, and WR implies the number of rows, number of ones in the rows, every rows of the parity check matrix. So WC is nothing but fixed number of ones in every columns of the parity check matrix, and WR implies a fixed number of ones in every row of this parity check matrix. Remember, every row will be having those fixed number of ones. The positions will be differing, obviously, but it will have only fixed number of, say, for example, first row will be having, say, only three ones. Second row will also be having 3 ones. Similarly, the first column will be having 4 ones. The second column will also be having 4 ones. Just for an example I'm giving. So if the number of ones in these rows and columns are fixed, which is equal in every column as well as every row, we will call it as a regular Ldpc code. And if this constraint is violated, or if this condition is violated, then we will call it as a irregular codes. Okay, so as I mentioned, it consists of small number of fixed ones. Okay, basically WC, which is greater than or equal to 3, which is a thumb rule which they used to give, and each row contains a fixed number of ones. Usually WR is greater than or equal to WC. Okay, the sparse.
I have a question.
Yes.
Sir, I am Raghava from Hyderabad. I have a question here.
Yeah.
So as this data is, so the parity is driven by the data, right? The content present in the information.
Yes.
So obviously, how can we impose sparsity on parity bits?
No,
as it is data driven.
No, it is data driven. Parity, no, in the sense, see, it will not be totally zeros, right? There will be fixed number of ones. It is not fixed numbers means here we have given it as 3 or 4. That is for a defined parity check. Okay, usually the size is very high. Okay, so usually the size is very high. So you would be observing sparsity property, but not entirely zeros. That can definitely, no, I didn't understand the point. No, I will take an example definitely, and I will show you at least for a general matrix how it would be. So okay, so it would be because it helps you in generating the parity. It will not affect your thing. Basically, your message bits or the parity bits will be definitely generated as a linear combination of message bits, definitely. Okay, because you will be having ones across the columns, so that will definitely make you to generate the parity bits for sure. However, the number of rows which you would be assuming here would be very large, so that definitely the message bits will drive this parity check bits. It is not very small kind of a parity check matrix which you are going to assume. Okay, the Ldpc codes will work better when your matrix size is very, very large. It is not just a small set of matrix, say 3x4 matrix or 5x7 matrix like a block code, and then you would be assuming only 1 or 2 ones across. No, it is not. So it is going to be at least a very huge size of matrix which is going to play, so that at least you'll be having fixed number of ones in that which can drive the parity. It is not going to affect that in any way. Okay. Okay.
Yes, sir. Yes, sir.
Okay. Okay. So this sparse here implies this number of columns is very, very less than or equal to this m, which is nothing but they say in this case this H matrix is nothing but m cross n matrix, m rows and n columns. Okay, so this number of that is what is this condition. This number of ones in this column should be very, very less than or equal to the number of rows which you are considering. Remember, for this Ldpc codes, you will be considering a very higher number of rows and columns. Okay, the message block length is also going to be very, very higher. That is what I have given, what Shannon envisioned. Okay, there is going to be a code which is going to be proposed with a higher block length, which is going to achieve a Shannon's capacity. Remember that fact. Anyway. So, and so the sparsity implies this condition basically, and the number of fixed number of ones in this rows is also going to be very, very less than or equal to n. And basically this tenor graph is going to probably it is going to represent this parity check matrix in terms of a graph, which will be very useful while you are decoding the information. Okay, this tenor graph visualization of parity check matrix. Okay, it is going to very much helpful while decoding this while decoding the Ldpc codes. And it is a bipartite graph in which the nodes can be, it is going to partitioned into 2 classes, and there is a condition that no edge can connect nodes within the same class. Probably this information might not be clear as of now. I will be going to show a tenor graph representation of an example parity check matrix so that it would be clear. So basically in the tenor graph, there will be 2 nodes involved. One is bit nodes, that is corresponding to n bits in the code word. Another one is check node, that is corresponding to m parity check equations. See, remember, this H is a m cross n matrix, right? So it will be comprising of m rows and n columns. Remember that fact. It comprises of m rows and n columns. In this m rows, you can see it as a m parity check constraints. Okay, and then this n columns corresponds to the n bits. Okay, so what is the parity check constraint? Probably we are going to take an example and then we are going to show it. Okay, now coming into this tenor graph representation, this is one example of a parity check matrix. Okay, this is indeed a regular Ldpc code. So you can see that 3 ones is there across every columns, and across every rows you could able to see 6 ones. So that is why it is regular Ldpc code, and you can say that the number of columns is also equal to 12. Okay, so there are 2 nodes I mentioned. One is bit nodes and check nodes. So this is nothing but your check nodes, this square representation, and this is nothing but your bit nodes, right? So this, sorry. So yes, so bit nodes, and you can see that the bit nodes will be equal to 12. This corresponds to the coded bits, and the check nodes implies the number of rows in this parity check matrix. Okay, so and you can see that see, if this is that check node, basically this is the first check node, means the first parity check constraint. Okay, how many what are all the bit informations which is involved? The first bit node, second bit node, third bit node, then 4th and 5th will be 0, then 6th, 7th, and then 11th. That's what you can see, that first, second, third. Okay, and then you could see that this 5th, you can see the connection, 5th, 6th, and then the 11th. So this, all this 1, 2, 3, 4, 5, 6 bit nodes will be involved or connected to this one check node. Similarly, in the second check node, that is the second parity check constraint, you would be seeing another 6 bit nodes will be connected to this check node. That's what it has been mentioned over here, that each parity check constraint means you have to visualize this at each rows. Okay, every row is a parity check constraint. Okay, involves WR code bits, right? this parity check first row, okay, that's the first parity check constraint, involves how many code bits? 1, 2, 3, 4, 5, 6. That 6 is nothing but WR. That's what it is mentioned. WR code bits. And each code bit now is involved in WC constraints. Means you have to now visualize the column, each code bit. So this is the corresponding code bits you can associate. So C4, C5, etc. Each code bit, C1, will be involved in how many constraints? WC constraints. See, in the first row it is involved, in the second row it is involved, and in the fourth row it is involved. So 3 constraints. So that is what WC constraints. Okay, and that is an additional information. The total number of ones is nothing but the fixed number of ones across columns multiplied with the number of columns. That will give you the total number of ones, which also you can compute from the fixed number of ones across the rows times the number of rows in the parity check matrix. That is also fine. Okay, now the rate of this Ldpc codes, basically you could able to evaluate, assuming this H matrix is having a linearly independent rows, which is not a very strict constraint in Ldpc codes. Okay, it need not be, but assuming that all these rows are linearly independent, this rate is nothing but R, which is equal to 1 minus m by n. Okay, basically rate of the code is nothing but k by n. Okay, so here you can assume this as this m is nothing but n minus k. M cross n parity check matrix, right? M means it is n minus k. Okay, so 1 minus n minus k divided by n. If you rearrange, it would be k by n. Okay, 1 minus m by n can also be written as, from this relation, WC times n is equal to WR times n. So that also can be written as 1 minus WC by WR. So that is the rate of the Ldpc codes. Now coming into the coded bits or the tenor graph representation, how you are going to visualize it. Now assuming this as code word C, which is having the parity check bits P1, P2, P3, and then the message bits M1, M2, M3, M4. Basically this kind of code words, they call it as a systematic code word, as the message bits is appearing entirely in the code word. Anyway, and the parity matrix, let us say we have assumed this sort of a parity check matrix. This may not be an Ldpc or which satisfies the conditions of the regular Ldpc code, which I am saying, just to give some example of a parity check to show you what is this parity check constraints are, and to visualize how this parity check constraint can be visualized as a single parity check code, which would help us in decoding this Ldpc codes. Okay, so this HC transpose is equal to 0. That is the constraint which is to be satisfied when you multiply this H with the C transport. You will be getting these 3 equations, and these 3 equations are nothing but the parity check constraints. Parity check constraints means what can be done? It is like M1, M2, M4, and this P1 can be brought in the other side. Remember this plus is XOR, provided this message bits are all binary bits. Okay, so you can rewrite this as M1 plus M2 plus M4 is equal to P1. Okay, remember it is an XOR addition. That is why -1 is also equal to +1 in terms of XOR. So you could able to see that with the combination of message bits, you can indeed generate the parity bits. M1, M3, M4 will be P2, and M2, M3, M4 will be P3. Okay, so this is what is the parity check constraints, which I am probably saying about. See, the number of parity check constraints obviously will be equal to the number of rows over here. And one interesting thing to be noted is, see, this first parity check constraint, that is P1 plus M1 plus M2 plus M4, that can be visualized as this M1, M2, M4, P1. There is 3 message bits and 1 parity check bits, and this 1 parity is generated by the linear combination of this M1, M2, M4, right? So there is 3 message bits and 1 parity bit. Okay, and this 1 parity is generated by the linear combination of this message bits and this code, which has a single parity, and that parity is generated based on the linear combination of other message bits, is what is called as a single parity check code. Okay, single parity check code. Okay, this is another set of code. However, we are visualizing each parity check constraint involved in the Ldpc code as a single parity check codes. Okay, so this visualization of Ldpc code as M SPC code. M means M number of parity check constraints will be there, right? Because M is the rows, number of rows. So every row will be corresponding to a parity check constraint. So this M single parity check code, you will be visualizing every row as a M parity check constraint. Okay, so which will be helpful, very well be helpful in the decoding the Ldpc code. This visualization of a single parity check code will be immensely helpful to decode the Ldpc code. Probably we are going to see that at least using a simple example. Now, giving some additional information compared to an Ldpc code, obviously this Ldpc code achieves better performance compared to the turbo codes, which is the previous codes which has been proposed based on parallel concatenation of recursive systematic convolutional codes. And it is now, you see, they are considering a Shannon's limit. Basically, I would also ask you to go through what is Shannon limit. It is, would say that minus 1.6 dB is the minimum SNR which is required to achieve an noise-free communication. Less than minus 1.6 dB of Shannon limit, you could not able to achieve a noise-free communication. That is what to say least about this. And this limit of minus 1.6 dB is a theoretical bound given by the Shannon. That is what they call it as a Shannon's limit. And every code which they are proposing, they will be comparing with this Shannon's limit. Basically, it is a theoretical bound, and practical bound, they will consider it as, say, 0.2 dB at error rate of 10 to the power of minus 7. Okay, so you could able to achieve the error rate of 10 to the power of minus 7 at the SNR value of 0.2 dB. That is the ideal or the practical or pragmatic Shannon's limit. Okay, so instead of minus 1.6, it is 0.2, and they would compare with this bound. For example, to say, this turbo codes achieve 10 to the power of minus 6 bit error rate at 0.7 dB. 0.7 dB, okay, which is 0.5 dB away from the Shannon's limit. And you can even see that this Ldpc code will be 0.0045 dB away from the Shannon's limit at an error rate of 10 to the power of minus 6. Okay, over the conditions when you are assuming it as a binary AWGN channel with a very high block length of 10 to the power of 7, message block length of 10 to the power of 7. Under these conditions, yes, indeed, it is getting closer to the Shannon's limit. That is one additional information. Now, there is a way to construct this Ldpc codes. Basically, I would be skipping this as a time constraint is there. So there is a Gallagher's way construction of this. Basically, that construction is with respect to the construction of parity check matrix. How to construct a parity check matrix with the fixed number of ones across columns and rows, and that indeed also should satisfy the sparsity constraint. Okay, so there are different ways: McKay's construction, Gallagher's construction. Definitely, I would urge you to go through Linian Costello book on error correcting codes, which gives an additional information of how to construct this. Now, coming into the Ldpc codes in the standards, basically this 5G communication is not going to be the only standard which is going to be proposing or using this Ldpc codes. The other standards, DVB S2, IEEE 802.112, 2012, these two are wireless Wi-Fi standards. Fourth generation communication indeed is also using fourth generation, where here the parity check matrix construction is based on protograph construction. Protograph construction means basically a base matrix will be assumed, and this base matrices will be expanded using some expansion factor, which I will be explaining you to construct this parity check matrix. See, once the parity check matrix is constructed with that the conditions, then simply you have to using that parity check matrix also you could able to generate or find the parity check bits, okay, which could able to frame your code word, right? How to find the parity check bits using the parity check matrix, that I have already shown you. Like CH transpose is equal to 0, and you could able to probably generate this parity bits using the message bits, using this constraint CH transpose is equal to 0. See, in order to find the parity check bits, either you can use a generator matrix based construction or as well as a parity check matrix, but Ldpc codes is completely driven by the parity check codes, basically, parity check matrix. Okay, that is why it is called as low density parity check code. Anyway, the construction of this parity check matrix can be through base graphs, or it is called as a base matrices, which is expanded using an expansion factor. How it is going to expand it, that is I'm going to say probably in the next 1 or 2 slides. And in 5G in our new radio, there are 2 base graphs which is assumed with several expansion factors that we will be seeing it. Okay. Now let us consider a simple base graph or base matrices, and assuming this base graph or base matrices is having an expansion factor of 5. If it is having an expansion factor of 5, then this base matrices will be having the entries ranging from -1, 0, 1 up to 4. Okay, so Yes, up to 4. So this will be the entries of this base matrix. So what this entries corresponds to? Okay, so for example, this 0 entry, it corresponds to a 5 cross 5 identity matrix. Why 5 cross 5? Because the expansion factor is 5. Okay, so 0 will be replaced by, you have to imagine this 0 will be replaced by a 5 cross 5 identity matrix. So then what? Minus 1? Minus 1 will be replaced by 5 cross 5 all 0 matrix. Then what is 1? Then 1 will be replaced by right shifting the identity matrix by one place. Okay, so this is, say, if you are assuming it as an identity matrix, so right shifting means this will go over here and this will go over here and this will come over here, 0 0 1 1 0 0 and then 0 1 0. So this is right shifting one place. Okay, this 1 will be replaced by right shifting the identity matrix by one place, and this 2 will be replaced by right shifting the identity matrix by 2 places. Now you have to replace with those entries, okay, these entries with these right shifted identity matrices, and then with which you could able to construct a very large parity check matrix using a very smaller base matrix or base graph. This base graphs and these entries will be specified in this 5G standard. Okay, you can see that the 5G standard has the expansion factor up to 384. Imagine we are using 5 cross 5 just for example's sake, but for Ldpc code, it is up to 384 is being involved in this 5G. Okay, so there are 2 base matrices which are currently proposed for this 5G, which is base graph 1, which is having 46 cross 68 size. This is base graph. Remember, it is not a parity check matrix. And base graph 2, which is 42 cross 52. That is another base graph, and they have this structure. Basically, this they would have come across after so much of experiments and after so much of analysis. Okay, that's what I could say. Why this structure they have proposed? Probably this structure they would have achieved a better performance. That is what is this. This have this structure. What is this? A implies? A implies for a base graph 1. There are 2 base graphs I have pointed out, 1 and 2. 1 is involved 46 cross 68. Let us take an example of base graph 1. This A will be 4 cross 22 matrix. 4 rows and 22 columns. E will be 4 cross 4, and then this O will be 4 cross 42 all 0 matrix. Okay, now you count the number of columns. Okay, number of columns is 22 plus 4, 26 plus 42, it is 68. That is what is the number of columns in the base graphs of BG1. Similarly, you can also check with the BG2. Okay, and this B corresponds to 42 cross 22 matrix. What are all these entries corresponding to this matrix A, E, the submatrices? These entries will be either starting from -1 to this expansion factor -1. Those will be the entries. Okay, that I have already given. So those entries are also specified in the 5GNR, that this should be the entries for this expansion factor. That is also being specified in the specifications document of this 5GNR. Okay, so only thing is this O matrix will be having all 0 matrix, and this I will be having, you can see it is 42 cross 42 identity matrix for BG1. Okay, so similarly you can the structure for BG2 is also given over here. And what is that expansion factor? It is represented by ZC, and that is given by A times 2J. And what is this J? That J ranges from 0 1 to JA. So JA and A are the 2 important parameters with which you could able to generate so many expansion factors, right? So that I have tabulated A and JA. It can be this should be the pair. This should be the pair which is given for 5G standard. This you should follow. So A can be 2 and then JA can be up to 7. So if A is 2 and JA is up to 7, then what will be the possible ZC values? So it would be 2 times 2 to the power of 0, which is 2. Then 2 times 2 to the power of 1, which is 4. In such a way, you could able to achieve an expansion factor up to 256. Given A and JA, you could able to see, you could able to get so many expansion factors. What is these expansion factors are going to play a role? Because this, according to this expansion factors only, the base matrix entries will be filled. That's what I have told. This base matrix entries will be -1 0 up to ZC -1, and maximum expansion factor for this 5G you can probably check with all these base matrices. With all these A and JA combinations, the base matrices maximum you would be achieving is 384. Okay, so that's what you have mentioned. Specific entries for this expansion factors corresponding to the base matrices are specified in this 5G standard document. this E matrix, that is going to play a very important role basically for encoding. Okay, and this E matrix alone, I am going to take it, and this will have this specific structure, which is called as a double diagonal structure. So you can see this 0, 0, 0 cross diagonal and 0, 0, 0. Remember what is 0 over here? 0 is an identity matrix. Remember that factor. Okay, -1 only corresponds to all 0 matrix, and 0 is an identity matrix. So it is having the structure that two diagonals and upper and lower part, there is a non-zero, that is 0 entries, and there is some other entries in this first column. So this sort of structure, basically what is called as a double diagonal, as you have double diagonal elements. So this will be definitely helpful in the encoding. How it is going to help in the encoding part of the Ldpc code, that I'm going to show you. Okay, so this E part in this block structure is very important, and point to be noted is they will be having a double diagonal structure, which is going to help you in encoding. Why this double diagonal structure? Probably this double diagonal structure they have incorporated, with which the better performance was achieved, and so they have incorporated inside this block structure. Without this double diagonal also, you could able to generate Ldpc code without much of a problem, but this double diagonal structure indeed helps them to achieve a better performance. That is why it has been specified as the block structure in this Ldpc code, or this base graph for this 5G NR standard. Okay, so and the message part, these are all with respect to the specifications. In this BG2 matrix, we'll be having this 10 into 48. 48 represents the expansion factors, right? Basically, you have to multiply the expansion factors with this message length in order to get the bits. Okay, so which means like every M1, M2 will be of, depending upon the expansion factor. Here, expansion factor is 48, which means M1 will be a 48-bit length, M2 will be a 48-bit length, and then M10 will be a 48-bit length, so that the message bit will be a 480 bits long, especially if the expansion factor is 5 in the case of a BG2 matrix. That is an information for you, that how much message bit they are considering, especially. That is for this case alone, that is BG2 matrix with the expansion factor of 48. Now coming how this encoding of using this double diagonal structure is going to help us out in how this double diagonal structure is going to help us in encoding this message bits using Ldpc code. Now we can see this is similar to that E matrix, right? This is an example matrix which I have taken, okay, parity check matrix, okay, which comprises of this double diagonal structure. You can see this I is nothing but what? 5 cross 5 identity matrix. Just for an example, I have taken the expansion factor as 5 and then going to show. I cannot show with 48-bit expansion factor, which will be very tedious. And this I also will be the identity matrix, and then you can compare with the previous double diagonal structure. The above and below elements, there it was -1. Obviously, -1 are all 0 matrix. Here I have given 0, which implies all 0 matrix. Okay, and then there involves some non-zero parameters in the first column. Similarly, you could able to see that structure in the previous slide, which I have shown. Now you can see, so this is the parity check matrix. Indeed, this I1 is nothing but identity matrix, column shifted one time. I2 is nothing but identity matrix with column shifted another time. Identity matrix of what length? 5 cross 5. Okay, so when you replace with all these, okay, with the details which I have given in this, okay, you would be getting a parity check matrix. Now, how it is going to help me? Yes, we are going to see this message M1, M2, M4, that each will be of 5 bits. How it is 5 bits? Yes, expansion factor is 5 bits, and code bit will be given by, this is the message bits which I'm considering, and this is the code bit M1, M2, M3, M4, P1, P2, P3, P4, and each message bits and code bit will be a 5-bit length depending upon the expansion factor. And we know that this parity check constraint should be satisfied, which means H times C transpose is this, and should be equal to 0. When you do this, HC transpose is equal to 0. Okay, there are 4 rows. I have considered only 4 rows of that matrix, and your first row will be like this. Second row, third row, and fourth row will be like this. You can see I1 times M1 and everything. It is there. Okay, basically you are having 2 parity check bits over here, P1, P2, each comprising of 5-bit length. Okay, now how I'm going to, basically HC transpose is going to give, should give me an information that what this parity check bits are going to be. Then only it will be helpful for encoding. Okay, P1, P2, P3, P4, I should know definitely it will be a linear combination of M1, M2, M3, M4, and how that linear combination is going to achieve, that information you will be getting when you are solving these 4 equations, which means what I'm doing is I'm just adding these 4 equations. When I'm adding these 4 equations, okay, I'll be getting a very big equation like this. You can perform it. Okay, it is an XOR addition. Adding in the sense it is an XOR addition. You can do the XORing and you will be getting this, where you can see that on the right side, you are getting one parity constraint, okay, P1, that is parity bit, means P1 will be a 5-bit length, remember. So P1 is a 5-bit length. So it is a parity. P1. So that is being generated, you can see, from the linear combination of all the message bits which has been given, okay, which we have considered, because we know the message blocks, right? PM1, M3, M4 message blocks of length 5 bits. Okay, so this P1, okay, can be generated, okay, P1 can be identified using the linear combination of all the other message blocks. And how it was achieved? By adding those 4 equations. How this structure I could able to get, because see, it is not standalone. First row, with the first row I could not able to find P1, P2 alone, right? Because M1, M3, M4 I know, but P1, P2 I don't know. Okay, second row obviously standalone. It cannot be. It cannot be a standalone. I could not able to find, okay, P2, P3 from M1, M2, M4. Obviously, I have to solve this 4 together in some way such that I could able to identify this P1, P2, P3, P4. Okay, that is what I have. I am solving it by just doing an addition. By doing an addition, all the other parity blocks are getting cancelled. Only P1 is remaining, from which I could able to find this P1 parity block, which is a 5-bit length, using message blocks M1, M2, M3, and M4, which is as given in this equation. How this structure has come? Because I have assumed my E as a double diagonal structure. This I have this parity P1 I could able to identify. Now I have identified P1. Now how I can identify the other parity? Fine. You know P1. Now you substitute P1 in this first row. If you know P1, obviously you know M1, M3, M4 message blocks. You substitute in this. Now you could able to find P2. Yes. Now I know P1 and P2. What I can do? You substitute P2 here, and then I can identify P3. Fine. Now I know P1, P2, P3. You substitute P1 and P3 in this third row. Get P4. Now you know P1, P2, P3, P4, and then with which you could able to identify all the parity check constraints. But the key point is the first parity information you could able to identify, so that helps you in identifying the subsequent parity bits only because you assumed a double diagonal structure in that. That helps you to achieve. This is especially with respect to a 5G NR standard, which is having a block structure which is of a double diagonal shape. It is not in general with respect to any LDPC encoding. Very simple encoding procedures are also there if it is not 5G. Very simple encoding with the you can able to do with this constraint of HC transpose is equal to 0. You can construct using a simple Gallagher construction, which I have given information about. You can use that, and then you could able to find the code word, which is very simple. But this is the standard which has been followed in this 5G to have a protograph or a base matrix structure, and the structure is also being specified. And in one of the structure, you have an E submatrix, which is a double diagonal structure, which is having a specific shape, and that helps you in identifying the parity bits. At least the first parity bit. If you identify the first parity bit, then using the parity check constraints or using the other rows, you could able to identify the subsequent parity bits. And I have mentioned already that it is important to have this structure to achieve better performance, especially at higher data rates. And you could see that why I have considered 4 rows, because that E matrix will be only coming up to 4 rows. If you specify, if you go to that structure, this E matrix, it's like only 4x4 matrix. Okay, that is why I have restricted my parity check matrix only to 4 rows. After this is going to be simply identity matrix. Simply identity matrix across the diagonal. You are going to have diagonal elements that helps you to generate all the other subsequent parity bits P5, P6, P6 without any problem. That parity check constraint itself will be a standalone. See, this is not, the first row is not standalone, right? Standalone in the sense with the help of first row alone, you could not able to identify the parity check bits, right? It should involve other rows also, so that you can solve and then find this, correct? But in 5th row, 6th row, and subsequent rows, it will be standalone. Using that row alone, okay, you could able to identify the subsequent parity bits or the parity blocks P5, P6, P7, which I have not given. Okay, so this is up to the encoding part. Yeah, we have some time left, at least 20 minutes time. At least we will see how the decoding part. Now, now the LDPC decoding, two very simple decoding techniques of other codes, other type of block codes are going to help us out in decoding the LDPC codes. What are all those? Which is a repetition code and single parity check code. Single parity check, we can imagine how it is going to help, because as I've already given an information that each parity check constraint or the each rows could be visualized as a single parity check code. Okay, so somehow the decoding of single parity check code, if I could able to decode a single parity check code, that information is going to help me out in decoding this. Similarly, a repetition code is also going to help me out. The decoding based on repetition code, okay, the decoding technique which is being followed for repetition code, that is also going to help me out in decoding this LDPC code. Probably I will go further. At least we will try to complete a decoding so that at least you will get an idea on how they are going to do it. Anyway, this is a simple block diagram which is for a repetition code. See, it is an encoder. It's a repetition code based encoder where it is having a bit m, and that is being encoded as m, right? That is what is repetition. 1 will be converted as 1, 1, 1, and 0 will be converted as 0, 0, 0, assuming it has a 3, 1 repetition code with the code word length of 3. Now what it will be done, you would be using a Bpsk scheme. So the Bpsk, it's going to convert this bit information 0 to symbol +1, and then it is going to convert this bit information 1 to symbol -1. This, remember, this +1 and -1 are symbols, and the 0 and 1 are bit. Okay, and that is going to get transmitted, and this is one model. Okay, you have to assume the assumption for this model is a symbol by symbol transmission, which is not usually the practical model, but you could able to imagine, you could able to relate it without much of a problem. This is a symbol by symbol transmission assumption. Okay, so an AWGen noise is getting added, and you would be receiving a real outputs. Because of this noise, this 1 and -1, you would be receiving it as a 0.3, 0.2, 0.1, or -0.4, 0.6, 0.7 in this way. So R is what is the real output. Now you will be using a decoder, especially I'm going to consider a soft input, soft output decoder. Soft input means basically this 0.1, which is having a range of values between 1 and -1. You will be having range of values. That is what is soft input. And I'm going to also output a soft, that is soft outputs. Again, this is not hard output. This decoder is not going to throw me strict ones or zeros. It is going to throw me again a soft output based on which I'm going to make a decision. Okay, so this soft input, soft decoder, and what is this Li? This is a belief that the corresponding CA is 0 or 1. And for a repetition code, this belief Li will be computed as L1, L2, and plus L3. What is this L1, L2, L3? Basically, this this Li, they implies the input channel log likelihood ratio. Okay, these involves LLR calculation and other things which is beyond the scope of this presentation. Basically, you could able to imagine this Li, which is L1, say for example, this is the belief for the first bit, which is nothing but L1 plus L2 plus L3. Okay, this L1 alone implies the intrinsic or the intrinsic LLR. Intrinsic LLR means this L1 is going to directly give me a good information about my coded bit C1. That is why it is intrinsic LLR. And this L2 and L3 is going to give additional information which I am going to make it based on this the code bit C1. Okay, that is why this L2, L3 for C1, okay, it is going to be extrinsic information. Similarly, this L2, the belief on second bit is also going to be L1 plus L2 plus L3. What is L1, L2, L3? Remember, L1 is proportional to R1. L2 is proportional to R2. How I have obtained this? Yes, using assumption of AWGen channel normal distribution, you could able to get this value. Probably I am skipping that out. Okay, so for L2, the small L2 will be the intrinsic information. That is a direct information or the belief which is giving you. That belief is going to help you in taking a decision for the C2. And this L1 and L3 indeed are going to help you out in making the decisions. Okay. So that's what I have mentioned over here. So this is the belief calculations, especially in case of a repetition code. In the same way, okay, considering a single parity check code. Single parity check code means you are having M1 and M2. Based on this M1 and M2, you are going to generate coded bit C3. So basically, the C is equal to M1, M2, and then P1. This P1 is nothing but M1 XOR with M2. Okay, so this coded bit C is C1 will be exactly the same message bit 1, C2 will be exactly the same message bit 2, and P1, the parity is generated, that is a single parity based on the previous two message bits M1 XOR with M2. That is what it implies. It is a single parity check code. It is a systematic coding, okay, as the message blocks are appearing directly. How here the LLR, this capital L which I have assumed now, that is output LLR. Basically, this is output LLR, which is nothing but the sum of the input or intrinsic LLR plus extrinsic LLR. Similarly, the output LLR is sum of intrinsic LLR plus extrinsic LLR. Intrinsic LLR is directly proportional to L1 for computing capital L1. It is directly proportional to R1. For extrinsic LLR, it is directly it is based on min sum decoder. The minimum of the absolute value of the other decoders, other LLR values will be this extrinsic LLRs. Okay, so based on this intrinsic and extrinsic LLR calculations, that is going to help us out in decoding the Ldpc codes. So the point to be noted is L1 is the intrinsic LLR for capital L1 output LLR. This output LLR is nothing but the belief which your belief on the first bit. For example, if this L1 is greater than or equal to 0, right, then you would decode it as say -1. Okay, you are going to take a decision, and L1 greater than less than or equal to 0, you could able to decode it as +1. So that is what. So that's what you're going to threshold it. Okay, based on this LLR values, and then you are going to make a decision on the received information bits. Okay, this belief. So this beliefs is nothing but intrinsic LLR plus extrinsic LLR, and this extrinsic LLR computation, especially in terms of SPC code, will be the minimum of the absolute value of other input LLRs. Input LLRs means other LLRs for bit 2 and bit 3, that is L2 and L3. So Lx2 will be nothing but minimum of absolute value of L1 comma L3. Okay, so this extrinsic LLR is nothing but absolute value of this Lxi, which is given over here, and then followed by a sign, and the sign of this first extrinsic LLR will be nothing but the product of sign of the other LLRs, L2 and L3. So for repetition code, it will be the LLR calculation will be simple addition. Here it is minimum of. This is called as a min sum decoder. After so many approximations, you will get a simplified structure or simplified equations for this. Anyway, this will help us out in visualizing the parity check constraint as a single parity check code, as well as visualizing it as a repetition code that helps us in decoding the Ldpc code. Okay, so this visualization is going to help us out, and as the time is proceeding, probably this min sum based and iterative message passing decoder, so that is going to help us out in doing the Ldpc decoding. And sir, can I take some 5 minutes time, sir? Or
Sure, sir. Sure. Please go ahead. This session is scheduled up to 11:30, so there is time, sir.
Okay,
please
so
go ahead.
at least I will finish off this example at least for them to give an idea. Okay. Okay. So
Yes.
this decoder, I will be slightly explaining it. Min sum, you could able to guess it. Obviously, the extrinsic LLR calculation for a single parity check code is based on that minimum of calculations which I have shown, right? That is what is min sum decoder. And iterative, basically there is going to be so many of iterations you are going to do it before decoding the Ldpc code. And message passing, the messages are going to pass between what? Between bit nodes and check nodes, and then the beliefs which will be getting updated, and based on that you are going to decode the information. Okay, just to give a simple example, say this is the code word, n-bit code word, okay, and this is the code word converted into a symbol information, -1 and 1. So basically Si is 1 minus 2 Ci. So if Ci is 0, then Si is going to be 1. If Ci is if Ca is 1, then Si is going to be -1, right? And this you assume it as a parity check matrix. I have shown only a part of the parity check matrix. I have not filled much of the columns. So you can see the this number indicates the column numbers, okay, or the corresponding bit nodes. You can assume 1, 2, 4, 6, 8, 10, 12. Or I have not indicated the intermediate values, as it will be zeros. That is why. Similarly, this indicates the row number 159. So the other things you can fill it as 0. Only this sparse ones need to be considered. Now, based on this, how you can form this parity check constraint? We know that H3 transpose is equal to 0. Based on that, you could able to write C1 plus C4 plus C8 plus C12, because the first row C1, C4, C8, C12, that will be equal to 0, because, and based on fifth row it will be C1, C2, C10, C20. Based on that you could able to write. Okay, so this row 1, row 5, row 9, you can individually imagine it as a single parity check code. Okay, so now coming into the part, you would be using a Tanner graph. Okay, for the bit nodes, there are 20 bit nodes. You have mentioned it over here. There are check nodes over here, and you are going to iterate it, and some extrinsic LLR informations are going to pass from bit nodes to check nodes. Similarly, some other extrinsic LLR going to pass from check nodes to bit nodes. You are going to update the beliefs which you are going to receive, and then you are going to take a decision for LDPC decoding. Okay, so basically the first iteration in the Tanner graph is, basically this would receive all these real output values, R1, R4, R8, all those values, and that is this. So based on this R1, R4, you could able to calculate this intrinsic information Li, and that will be passed to from the bit node to the check nodes. Okay, that is a part of the first iteration. And so say 1 will be receiving, say, L1, L4, L8, and L12, right? So this first row, okay, it is having 4 beliefs, right? And you can visualize this first row, as I've already mentioned, as a single parity check code, and you know how to compute an extrinsic LLR for a single parity check code. What you will do, it would be based on minimum sum decoder, and you are going to, in order to calculate this information about L11, okay, which is this between this bit node, first bit node, and first check node, you are going to perform minimum of L4, L8, that is L4, L8, L12. Okay. Similarly, the other extrinsic LLR information can be computed. Similarly, that information, this L11, will be passed in the second iteration to in the first iteration, these extrinsic LLRs will be passed to the bit node, and in the bit node, based on this extrinsic LLR information, L11, L15, L19, all giving some information about the bit number 1, which is equivalent to viewing it as a repetition code. Basically, in repetition code, this M1, M2, M3, if it is a 3 code word length based repetition code, okay, this see 111, it is going to be 000. To decode the first message bit, obviously these 2 other message bits is also going to play a role. Okay, so in decoding the first, similarly the second message bits, these first and third is also going to play a role. That is how you have to visualize that these 3 extrinsic LLRs, okay, it is giving some information, okay, about the first bit, that you are going to visualize at the bit node end as a repetition code, and you are going to apply the calculation of extrinsic LLR for repetition code, and then you are going to compute M11, M15, M19. So M11, how it can be computed? It can be computed as other extrinsic LLR. You should not include this L11. You should consider L15, L19 plus L1. You are going to consider this extrinsic LLR information. This is based on the repetition code, which I have shown before. Okay, so that is going to be computed, and this information is going to be passed from bit node to check node. And then in the second iteration, similarly, this check node is going to receive this LLR informations, that is M11, M15, M19, okay. And then they are going to view it as a single parity check code. And then again, the extrinsic LLR computation will be based on a single parity check code. That LLR will be passed to the bit node. In the same way, it is going to pass on the message, and then the beliefs, this R1, R2, R3, based on this LLRs will be updated as R1 prime, R2 prime, R3 prime, and then you are going to perform a thresholding based on which you are going to take the decision, which has been shown in this example. I would urge you to go through this example. Okay, so at least probably you would get some idea, but basically this is an iterative procedure, right? So first iteration, second iteration, these iterations are going to, if you are performing more iterations, probably that indeed is going to make your performance or make your decisions better. Probably it can able to improve this, improve the efficiency. Basically, see, you have to visualize this that for a large block length, of course, sophisticated decoders have been proposed so that simultaneous operations can be carried out, so that you would not ending up in complexity based things. Okay, that has been taken care of already. So this kind of a message passing based and iteration based decoder, a soft input, soft output decoder is being proposed for LDPC code. codes. Okay, so probably I don't have time to go through this, so I have spent at least I believe I spent enough time on this Ldpc at least to give the Polar codes just an introduction. I will finish off. It would be for the control channel. This Polar codes is based. It is completely a different phenomena. It is based on something called as channel polarization, where a channel which is having a fixed noise, because of the channel polarization, it is going to get converted into very noisy channel and as well as noiseless channel. Okay, it is going to this channel polarization technique, or this polar transform, is going to convert a channel with a given SNR, okay, given SNR into a very noisy channel and very noiseless channel. The SNR is fixed, but it is going to push the channel into very noisy and very noiseless bit channels, and you are going to transmit the information across the bit channels by selecting the bit channels which is having a noiseless channel. Okay, so it is going to convert it given channel into group of bit channels, and specific group of bit channels will be noisy, very noisy, and specific group of bit channels will be very noiseless. There is a technique for that. There is polar transform. That is what is Polar code. And since it is converting a given channel into very noisy and noiseless, that is polarizing it, and you are going to choose your bit positions, okay, and you are going to transmit only through that noiseless bit channels, and that noisy bit channels you are going to frozen it, okay, with which you could able to achieve a comparable performance with that of the Ldpc code for a higher block length. That is fixed. Your block length should be higher, so that when you are using, there are also a few decoders available: successive cancellation decoder, SCD decoder, and list decoding. So probably SCD is very simple and it is suboptimal, and the list decoding is kind of an optimal decoding with which you could get a comparable performance with that of the Ldpc codes. Okay, so it relies more on the channel polarization and other techniques, Kronecker or tensor product based techniques, which you can go through. And I will also urge you to go through these references. Basically, I have taken this from the, there is an exclusive NPTEL course available on Ldpc and Polar codes for 5G standard by Professor Andrew Thangaraj. So major part of that I have studied, I have undergone that courses and then taken it from there and I have presented it. Similarly, there is to get an introduction about this coding theory, there is also a lecture notes available or NPTEL course available from Professor Adrish Banerjee that you can also go through. And Linen Costello basically doesn't have information on Polar codes. Even in the recent edition, it have information up to Ldpc codes, various construction of Ldpc codes, and how Ldpc codes can be decoded using this message passing iterative algorithms. That is also there. And there is also one important link which you can go through where you would find sufficient information about Polar codes. This is from the group of Emmanuel Viterbo. So this is he's one of my friend, Harish Vangala. He worked immensely on this Polar codes, and he has given a presentation as well as a video tutorial for this Polar codes and encoding and decoding techniques, which you also can go through. Okay, so with this note, probably I will finish off, and questions are invited.
Yeah, thank you, sir. Sir, just keep your presentation on. Can you just go to your second last, I mean, your third last, the slide before this, sir? Yeah, advantages. Yeah.
So basically, advantages, especially in the aspect of Polar codes, it is quite easier to implement with high hardware efficiency. But the problem is you can achieve best performance, that's what I told, under an advanced decoders. Advanced decoder means this list decoding will be coming in the advanced decoders. So SCD decoder is, it is very simple to implement, but it may not give you the required performance which you are expecting. That is one. As well as the advantages is basically you won't encounter an error flows, especially when you are transmitting over a binary symmetric or erasure channel. But coming into the disadvantages, as I mentioned, it performs poorer under successive cancellation decoder compared to Ldpc code for a finite block length n. And to obtain an improved performance, obviously you have to go for sophisticated decoders, advanced decoders. And when you're going for the advanced decoders, probably the solutions, the implementations is going to be costlier. That is how the trade-off is.
Yeah, thank you, sir. I think that answers the question which was posted there by Vinod. Any other questions? You can please, participant may please type in the chat box, or else I think Dr. Swaminathan also has another engagement now, which is running parallelly. So any more questions? All right, sir. So I think you have pretty comprehensively covered most of the aspects. In fact, you went into great deal of depth when it comes to uh, uh, LDPC code. So I thank you, sir. So there is one question. I think it is similar to the question which was asked before. That is, if you look at the SNR versus BER graph.
Yes, I have not shown that. I have not
Yeah.
shown that. Probably you would encounter it. Yeah, that I have given some additional information compared to Shannon's limit, how it is slightly away the LDPC codes. Basically, it would be something like that. I could, obviously, it will be slightly 1 dB or 2 dB or like 0.0045. That is an ideal one. At least if it is of a very decent block length, you could be able to achieve away from the Shannon's limit of 0.04 dB. So we can't give a rough plot over here, at least for comparative sake, I can give, but this is the important information. Around 0.04 dB, it will be away from the Shannon's limit for LDPC code to achieve a bit error rate of 10 to the power of -6 for a block length of 10 to the power of 7. Basically, if you are assuming this as a, for comparison sake, without values, if I want to write, if it is a base graph 1, if you are showing, then you could able to see that this is for LDPC code base graph 1. Somehow you would achieve something like this for polar codes, basically. So if it is like this, the polar code will be having this sort of, in the low SNR, the polar code is deteriorating, and in the high SNR, it is performing better than the LDPC codes base graph 1. Okay, and then if you're considering this as the polar code, and polar code based on list coding, I have told that you can achieve best performance under list coding. You would end up getting like this for an SED, that is successive cancellation decoder, which performs poorer compared to the list decoding. So when you want to have a comparable performance, which I've already mentioned for the LDPC code, when you want to have a comparable performance for the polar codes, obviously you have to use an advanced decoders, possibly list decoding. Okay, that is one such advanced decoder with which you could able to get a comparable performance with respect to an LDPC code, so that for one certain SNR range, polar code will be performing better, and some other SNR range, an LDPC code will be performing better, so that they have used these two codes, LDPC for data channel and polar codes for the control channel in case of 5G communications.
Yes, sir. So that also answers Vikas Gupta's question. So, sir, I really thank you from the bottom of my heart. In fact, channel coding itself is a very challenging area, and moreover, for 5, you have explained it in the context of 5G. So thank you so much, sir, on behalf of the participants, Atal Academy and Goa College of Engineering. I sincerely thank you for being with us today, and the passion with which you teach is fantastic. And 85% of our participants are teachers, and
Okay.
and you are seriously, I mean, a wonderful role model for all of us. So on that note, on that note, I'll wind up this session.
Just one
Thank you,
additional
sir, once
information.
again.
Yes.
Sure.
Yes,
Yes, sir. Please go ahead. Please.
Yes,
Yeah.
For all the other participants, thank you, and I should thank Dr. Shahjahan Kuti as well as Dr. Prabhu Chandar, who's my senior and who's also there, who's a director of Chandar Research Labs, who's also part of this FDP, was also one of the organizers for this FDP. I also thank him. And similar along this line, IIT Indore, we are also going to organize one 5G communications workshop, 5G wireless, 5G and beyond wireless techniques, where the coordinator is myself, and then subsequently other faculty members are also going to give an invited lectures. So it's going to be a 3-day online FDP course, which is going to be from December 21 to 24, which I have planned, for which I'm circulating the brochures. So I will also circulate to Dr. Shahjahan Kuti. Probably he might also share it with you. So for TechWhip 3, it is sponsored by TechWhip 3. So if your institute is TechWhip 3 funded, it is free. You can register for this course and attend. If it is not TechWhip funded, of course, for faculty, a very nominal charge of rupees 3,000. I have kept it for 3-day workshop, and it also involves a bit of MATLAB sessions to give you at least an idea of how to. Especially it will be concentrating on 5G and beyond wireless technologies, very many physical layer techniques such as spatial modulation and optical wireless, and indeed few other topics such as energy harvesting with cognitive radio, visible light communications. It is 5G as well as beyond 5G. What are all the futuristic communication technologies which are going to get which are going to come. So those, it's going to be addressed in a 3-day online FTP program. I will circulate